All right, today, lesson 29B, geometric sequences. Earlier in the year, in Unit 2, we talked about arithmetic sequences, which were based on linear functions. Today, we talk about geometric sequences, which are based on exponential functions, and we'll also talk about how to determine the difference between arithmetic and geometric sequences. So let's go ahead and get started. Like I just mentioned, in Unit 2, we first encountered sequences which just consisted of a pattern of numbers in a particular order. We studied the idea of an arithmetic sequence where each successive number in the list was generated by adding the same quantity to the previous number. In other words, it's a number pattern where you're adding on the same number each time. And so just to quickly refresh your memory, here's number one. An arithmetic sequence is defined explicitly by the following formula. And that kind of equation should look very familiar to you. It's an equation in slope-intercept form. And we use that same strategy to find explicit formulas for arithmetic sequences. So what I want you to do is I want you to find the first three terms in that sequence. Now, in case you have forgotten how to do that, here's how we did it earlier in there. We said a sub 1 is equal to, and what that means is that we substituted 1 in for x and simplified. So that means that the first term in the sequence is 5. So the first term is 5. Go ahead and find the next two terms in that sequence. So the first term in the sequence is 5. The second term in the sequence, by substituting 2 in for x, is 8. The third term, by substituting 3 in for x, we get 11. And you can see we are adding 3 on to each term to find the next term, which of course comes from the slope. Now, that's the first term, the second term, and the third term. The next thing in your notes, it says to you to find the value of a sub 20. A sub 20, remember, is a shortcut way of asking you to find the 20th term in the sequence. And we could keep adding on 3 every time until we got the 20th term, but that takes a long time. You should easily know how to find the 20th term. So quickly find the 20th term in that sequence. And what is it? It's 62. Okay? So that's a quick refresher of how to deal with arithmetic sequences. Now part C is asking for the initial value. What is the initial value? It's 2. It's the y-intercept. And in a real-world problem, that would be called the 0 term, which when we're talking about arithmetic sequences, we really aren't as concerned about the 0 term. We're more concerned about what the actual first term is. But remember, the initial value in an arithmetic sequence is the y-intercept. All right. Arithmetic sequences share many characteristics of linear functions. In fact, arithmetic sequences are examples of discrete linear functions. Remember, a discrete linear function is one where it doesn't make sense when you graph to connect your dots together, connect your ordered pairs together. Exponential functions have their own discrete versions, and those are called geometric sequences. They also have an explicit formula, and obviously, in this part right here, you are filling in things in your notes. Now, if you look at the explicit formula for geometric sequences, it looks almost identical to the exponential function formula. Quickly turn to your shoulder partner and talk about what's different with this compared to exponential functions. So, y is the term that you are trying to find. Make sure you add that to your notes. And that's true even in an arithmetic sequence. In the exponential functions, a was always the initial value, which is the 0 term. But we're not concerned as much about the 0 term in geometric sequences. So a is not the initial value or the 0 term. It is the first term or the first value. And that's why the exponent is not x. That's why it's x minus 1. b, like in exponential functions, is the multiply factor or the multiply number or the base. With geometric sequences, we refer to it as the common ratio. So we're going to throw those two terms around a lot. Multiply factor, common ratio, they're really referring to the same thing. And then this x minus 1 is, of course, our exponent. And it's x minus 1 instead of x because we are starting at the first term and not the 0 term, which is the initial value. I'm going to stop for a second to let everybody get caught up. All right, so continuing on. In both arithmetic and geometric sequences, which remember are just really number patterns, we are less concerned about the 0 term than we are in real-world problems like we had been working on the previous 3 or 4 lessons. We're starting at the first value or the first term in geometric sequences. And a little bit of background knowledge. This is a problem we talked about yesterday. This is not in your notes, I don't think. But this is a problem from yesterday. And once again, in geometric sequences and in arithmetic sequences, we are not as concerned about that initial value there. We're usually starting at the first value or the first term. So let's sort of piece all this together before we actually start with a problem. Function and sequence review. So you've got some things you need to add to your notes here. Linear functions are all in this slope-intercept form, y equals mx plus b. Exponential functions look like this. Y equals a times b to the x power. Linear functions can be either discrete or continuous. And we saw lots of both of them. Exponential functions can be discrete or continuous. When we're referring to arithmetic sequences, the equation that we use is identical to linear functions. It is y equals mx plus b. But with arithmetic sequences, they are only discretes. And my biggest concern with geometric sequences is some of you going back to that exponential function formula. That's not going to work as nicely for us. We need to remember that we're using to the x minus 1 power if we're referring to a geometric sequence. And like arithmetic sequences, geometric sequences are only discrete. All right, so let's go down to number 2, where I'm going to start giving you some sequences, and you've got to find the next couple of terms and then tell me what the common ratio is and then come up with an explicit formula. So let's go ahead and go. Here is number 2, part A. Find the next 2 terms. Find the common ratio, r. Remember, r, the common ratio, is really just the multiplying factor. And then from that, come up with the explicit formula. All right, what's the next term after 18? Just say it, please. 54. And then after 54? All right, remember, r is called the common ratio when we're talking about geometric sequences, but it's really just the multiplying factor. So what is r? Why is it 3? Raise your hand if you know. Why is it 3?
Because you're multiplying every time.
Yeah, it's the multiplying factor. You're multiplying every time by 3. So the common ratio r represents b, the multiply factor, in a geometric sequence. And so r is 3. So from there, we need to come up with our explicit formula. Remember, for geometric sequences, it is y equals a times b to the x minus 1 power. A is the first term. There's the first term. And b is the common ratio. So, from there, that leads us to our explicit formula of y equals 2 times 3 to the x minus 1 power. All right, go ahead and do the same exact thing for part B and part C. Look at part B and part C. Part B looks like this. We, of course, are multiplying each of the previous values by -5 to make the next value. So that makes the next number in our sequence -500 and then +2500. r, the common ratio, which really is the multiplying factor, is -5, and that's all we need to find the geometric sequence explicit formula. That would be y equals 4 times -5 to the x minus 1 power. Any questions with that one? All right, part C. Going from 16 to 8 to 4, we are multiplying by 1/2. So that makes the next two terms 2 and 1. The common ratio, which is the multiplying factor, is 1/2. That's all we need to come up with our explicit formula. So y equals 16 times 1/2 to the x minus 1 power. All right. Everybody do number 3, all 3 parts, and then we'll compare those with our shoulder partner. You've got about 45 more seconds to finish up all 3 parts of number 3. In this sequence, I'm telling you the first term is 3 and the common ratio or the multiplying factor is 2. That gives us an explicit formula of this right here. That should be obvious. That helps us find part B and part C. For part B, you're finding the second term, third term, fourth term. Second term is 6. Third term is 12. Fourth term is 24. Any questions on how we get those 3? If you've got that, then part C is just as easy. For part C, we're finding the 10th term, so we're going to do 3 times 2 to the 9th power because we have x minus 1 for our exponent. And that would give us 1,536. And then the 20th term, that's going to be 3 times 2 to the 19th power. That would be 1,572,864. So any questions about number 3? All right. As we noticed yesterday, exponential functions grow much faster than linear functions. The same is true when comparing geometric sequences to arithmetic sequences. So let's go to number 4. You have just won a very strange lottery. The lottery promises to give you money each day for a 30-day month based on one of 2 options. Option number 1, you can receive $1,000 the first day, $2,000 the second day, $3,000 the third day, and so on. And that's an example of an arithmetic sequence because each day you receive $1,000 more. Or you can receive option number 2, where you receive a penny on the first day, 2 cents on the second day, 4 cents on the third day, 8 cents on the fourth day. How much would you get on the 5th day? 16 cents. So in other words, the amount you're receiving doubles each day. That's an example, of course, of a geometric sequence. So in your notes, you have these tables where you can log 30 days for each option. Now, before you even start, I want you to make a guess on which option is going to be the better of the 2. Because if we're pretending like you won the lottery and you had your choice, I want to know which choice you would take. Okay? All right, so with your shoulder partner, I want you to fill in your tables and figure out at what point option 2 obviously becomes the better deal. I'm going to give you about 5 minutes to get both these tables filled out. So remember, of the 2 options, which would result in a larger payoff on the 30th day? That's basically what we're trying to figure out. And showing work means filling out the tables until it becomes obvious which one is going to give you more money on day number 30. All right, so what we're trying to do once again is we're trying to figure out which one has the larger payoff on the 30th day only. Option 1 obviously is $30,000, but option 2, as we will see right here, is right there, a very large number. And I had to go really small font, but it looks like it is $5,368,709.12. So they're not even close to one another. And what this is basically another example on how quickly exponential functions, the rate of change, how much faster they grow than linear functions. Because the one on the left is an arithmetic sequence, which is a linear function, and the one on the right is an exponential function, which is a geometric sequence. Okay? All right. Problem number 5. We've got 2 problems left. For a geometric sequence, with a first term of 16 and a common ratio of 1/2, list and plot the first 6 terms on the grid below. I'll kind of get you started with a table. The first term, as it says up there in the first sentence, is 16. The second term will have a common ratio of 1/2. What would the second term be? Just say it quickly.
8.
8. All right, go ahead and finish it off and plot. And there's a point to this problem, and I'm going to see how many of you remember something we've talked about during the last 2 days. All right, the point to this problem is very simple. How many of you were listening about something that I talked about earlier in this lesson, and we ran into it when we were correcting the homework assignment from yesterday? And that is this. Probably 40% of you connected the dots together. Why should we not connect the dots together in this, let me finish up the graph here. Why should I not?
Because a geometric sequence is discrete.
Yes. Arithmetic sequences represent discrete functions. Geometric sequences represent discrete functions. If you don't believe me, look back a few pages in your notes from today. This problem was not difficult. I just wanted to see who was going to connect them together and who was not going to connect them together. All right, last problem for today has 2 parts. And you are to do this. For each of the following, determine whether the sequence is arithmetic, geometric, or neither. Then find the explicit formula. So tell me whether it's arithmetic or geometric or neither. And if it is one of the 2, arithmetic or geometric, tell me what the explicit formula is. You've got about 2 minutes. All right, part A, fairly obvious that that's a geometric sequence. Our x values are increasing by the same number each time by 1, and then our y numbers are getting half smaller. So that's a geometric sequence, and the function is y equals 64 times 1/2 x to the minus 1 power. Nobody had any problems with that one. It was this one that was a little bit more of a problem here. But look, for the x values, we're adding 4. Y values, we're adding 2. Adding 4, adding 2, adding 4, adding 2. That tells us that it is an arithmetic sequence. And back when we first dealt with linear functions, this method is kind of how we figured out what the linear function should be. So the difference of the y's over the difference of the x's tells us that the slope has to be 1/2. Another way of thinking about this is you could create a larger table that follows the same exact pattern, and you fill in all the gaps like this. Now, I wouldn't expect any of you to do that, but that could get you down to find the initial value. But once you find the slope is 1/2, then you could use the point slope formula like we did a long time ago. But regardless of that, the explicit formula should be y equals 1/2 x plus 10. All right, we are finished.